In this segment, we're going to talk about wind and qualitatively its effects on the water column. A typical water column looks something like this. You have an area that's mixed by the wind. For example, in our scalar variable temperature, the temperature is fairly uniform here. And you have a deep water area where the temperature is more or less uniform but decreasing with depth. And you have an area over which the temperature's changing rapidly. In this region, the rate of change of temperature, dt dz, is large. The magnitude of that is large. This area over which the temperature changes rapidly is known as the thermocline. If this were a salinity plot, that would be a halocline. And in terms of density, it is a pycnocline. So remember those terms. This shows water columns in a very broad sense across the world. In high latitudes, you have a very well mixed column, meaning that the properties vary very little within the water column. A few degrees of temperature, salinity, etc. That's because it's very well mixed. We've had enough cooling at the surface that we've produced the relatively uniform column. The tropics are the opposite of that. We have an area near the surface where the water is quite stratified, meaning we have warm water overlying colder water that is persistent essentially year-round. And at mid-latitudes, here, we have a cycle. The water column varies over the year. During the winter, it more approximates a northern latitude water column with weaker stratification, more mixing, more uniform properties in the vertical. And during summer, you have low density or warmer water at the surface, meaning you have a stratified water column which better approximates what's happening in the tropics. So there's a shifting back and forth in the mid-latitude regions of the water column. And this has to do with the seasonal cycles of heating and cooling, as well as seasonal winds. So what does heating and cooling do to a profile? Heating of the water column increases stratification. It increases the temperature, which decreases the density. And stratification means that we have lower density fluid overlying higher density fluid, meaning it is a more stable water column. And it's gone further from the case of having uniform density. With heating, we can reduce the density at the surface. So we can have lighter water overlying heavier water. This is from heating. Cooling does the opposite. It decreases stratification. So if you start with stratification, the density can increase as the temperature is decreasing. So that increasing density reduces stratification because the density of the surface layer starts approaching that of the bottom layer, tending towards neutral stability. So cooling decreases stratification, decreases stability, and heating does the opposite. What about wind forcing? Wind puts a stress at the surface, as we discussed in the previous unit. It tends to mix up the upper water column. This energy from mixing ultimately comes from the wind, but of course the wind energy comes ultimately from the sun, so we can think of this as like solar energy, but in direct sense it's from the wind. In our region it's pretty seasonal. We have strongest winds in the fall and spring. The fall we have big northwest winds. We have systems moving through in the spring, but very near the coast we also have strong winds during the summer because of our persistent sea breeze. What this wind mixing tends to do is it tends to disturb the stratification, in the sense that it tries to mix up higher density waters into the lower density waters and vice versa. So if we start with a profile of low density over high, strong enough mechanical mixing can erode this profile to try to make it more uniform. Essentially, we have a competing effect because during the summer we have weak winds and strong heating, and that's what produces the stratification. The winds would like to destroy that stratification, but they are weak, and the heat forcing is increasing the stratification. Once fall starts, essentially September-ish, late September, we get cooler periods and stronger winds, and they start to erode the stratification until it arrives at a winter profile. And then once this following spring comes around and the winds start to get weaker again and the heating starts to increase, it will go back to its summer profile. This is an annual cycle in typical mid-latitude regions, including the Gulf of Maine. Cycle of winds, cycle of heat flux. Now, why doesn't the wind mix the whole column all the time into a polar column? And this comes down to an issue of stability. Stability, we'll just look at a simple two-layer water column where we have density rho 1 lighter than density rho 2, and a layer of this rho 1 overlying a layer of rho 2. And then we ask the question, how much work does it require to move this, this is per meter squared of surface area, to move a block of water from the rho 2 region up into the rho 1 region? How much work does that take to do? Because this is denser than this, it's going to take some effort. It's no different than lifting a block of iron into the air. Air has very low density, iron has very high density. It is difficult to do that. But if you take a block of iron and immerse it in a fluid of the same density, say liquid iron, it's easier. I guess you can move it up and down in that case because the density difference is very small. So the density difference is important. What else is important? Well, what's working against you? Gravity. So this has to come into play. And how far you're planning on moving it, a mile or a millimeter. So those three things have to be positively related to, just simple argument terms, to this potential energy. If you have to carry a package up a hill, the further you have to go, the more work it takes you to do. If you go to another planet where the gravity is very high, the more work it's going to take you to do. And this density is key. Because, for example, if the fluid is of one density, if rho 1 is equal to rho 2, you can move this box up and down without any work at all, ignoring friction. So this is where stratification comes in. The bigger this difference between rho 1 and rho 2, the more the water is stratified. More stratified water has bigger jumps in density, which means that this difference is bigger, which means we need more of this potential energy to get this parcel up here. The same argument goes for taking a parcel of the lighter water and pushing it down, similar to taking a basketball filled with air and trying to shove it down in the water. It takes work to do that because the basketball is lighter than the water. You could fill the basketball with water, pull it out of the water into the air. That is difficult to do too because of this, that comes down to a density difference. So here you're either pushing down our lighter parcel or pulling up our heavier parcel. Either way, the potential energy is proportional to these quantities. So the key thing is that it takes work to exchange parcels. And exchanging parcels is the same as mixing. If I wanted this whole region to be of the same density, which is equal to half rho 1 plus rho 2, I'd have to get a lot of these parcels up here and a lot of these parcels down here. To do that takes energy. Where does that energy come from? It comes from the wind. The wind is where that energy comes from. The wind induces mixing, turbulent mixing in the water column by imparting a stress on the surface. It produces a region of turbulent mixing in the upper water column. That mixing tries to create uniform properties everywhere, just like stirring your coffee with cream in it. Eventually you get uniform temperatures. We're taking liquids of two temperatures and stirring them together. You will stir it up. You'll have a liquid of uniform temperature. That is what the wind tries to do. However, the stratification, here we have, again, two-layer system, two different densities. If this mechanical mixing is not strong enough to do that exchange of parcels that we discussed, then the mixing will stop at where that gradient lies, essentially the thermocline or the pycnocline. This is, again, an idealized two-layer system. We can think of the real ocean, a stratified real ocean, in the sense of an idealized stratified flow. So with strong enough density gradient, the wind won't have the power to mix the water column. So that's essentially the battle. You have stratification, which comes from heating, fighting against mixing, which comes from wind. And who wins out really essentially depends on the season in a broad sense. During summer, heating wins out over the wind mixing. During winter, the wind heats out over the heat flux, which is in that sense is negative and is working with the wind. This has strong implications of biology. We'll discuss this more in detail later in the class. Essentially, there's a zone up here where primary production is occurring, photosynthesis is occurring because there's enough light. It requires nutrients. Those nutrients are used up by the primary production. And once those nutrients are used up, the new nutrients are unavailable to primary production. You only have recycled nutrients at that point. These deep water nutrients aren't available because they can't get mixed up into the area of primary production. And it takes until fall, when the water column is broken down and we can mix through this barrier essentially to bring up the deep water nutrients into the water column. If we still have enough light, the conditions may be right for a second bloom, a fall bloom in that case. If we get the right conditions of a strong windstorm early enough in the fall, it can drive a fall bloom. Either way, during the winter, everything gets mixed back up. And so it essentially refreshes these nutrients for the next March, April, spring bloom. And so that's an annual cycle of production that's enabled by the buildup and destruction of the stratification at mid-latitudes.